Let's consider the following dimensional analysis problem. Let's suppose that we have 60,000 miles and we want to know how many inches that correlates to. Now, let's think about this for a second. Miles are a pretty big unit. Inches are pretty small, so we're expecting a super big number response for this one. Let's try it out using our dimensional analysis process. Again, we start by writing our value over 1, like it's a fraction. Then I'm going to multiply to get rid of the miles. So since miles are in the numerator, we need to put miles in the denominator to divide out. On my conversion factor or conversion table or chart, I do have a conversion that shows that there's 5,280 feet in every mile. That gets my miles to divide out. I still want inches. Feet are on the top, so I'm going to put feet in the denominator. I want to change to inches. And I know that there's 12 inches in 1 foot. The feet units divide out, and I'm left just with inches as the only remaining unit in my problem. To get my answer then, I'm going to have to do 60,000 times by 5,280 times by 12 and divide by 1 in order to get my answer in inches. All right, well, let's pull out the calculator and do that. So here's my great iPhone, apparently with a little bit of a glare that I can't avoid. All right, so as we go through here, I'm going to do 60,000 times by 5,280 times by 12. And look at the answer response that my calculator is giving me here, 3.8016 E9. This little E value here is essentially telling me that my number that I put into my calculator is way too big, and the response that it's giving me is in scientific notation. Let me write this down here, and let's talk about it for just a second. 3.8016 E9. Now, depending on the calculator that you use, sometimes instead of E, you'll see this written as 3.8016, and you'll have a little EE like this. Other times, you'll just see the 3.8016, and then over on the far side of the screen, you might see something like 09 as a little number written above. All of these are different indications that show that the answer that you're getting is large and in scientific notation. Scientific notation is always written in this form. We have some number that's written first. This number is always between 1 and 10. It's okay for your number to be 1. It's not okay for your number to be 10. Essentially, what we really want to focus on here is the idea that there's just a single digit in front of the decimal. Okay, so in this case, my number between 1 and 10 is going to be this 3.8016 that's coming here. My B value up here is an exponent, and that's going to correlate with what the power of 10 is. Now, we love powers of 10 because our number system is based on 10 digits. So if you think back to maybe converting from decimals to percentages where you have to times by 100 and all you had to do was move the decimal point over, when something's written in this format, this number up here is going to tell you how many places that you need to move the decimal. If our B value is positive, it's going to make our number bigger or represent a bigger number. And by bigger, I just mean bigger than 10 because that's the number that we have over here. If our B is negative, then that's going to mean that our number value is smaller. And by that, I mean that it is less than 1. So here, if I have a negative exponent, it doesn't mean that my number is negative. A negative exponent power of 10 means that I am moving the decimal in a way that's going to make my number smaller. So let's take a look and bring back this number here. So if we were to write the value that we found on our calculator, we'd have 3.8016 times 10 to the 9th power. So if I want to figure out what that would be in what we call standard notation, which is not having something times 10 to a power, what I do is I start with my 3.8016, and I'm going to move the decimal in a way that's going to make my number bigger, and I'm going to move the decimal 9 places. All right, so let's try that. My decimal right now is here at 3.8016. I'm going to move it once, twice, 3 times, 4 times. I still have 5 more times to go. 1, 2, 3, 4, 5. So that gives me a total of 9 movements of the decimal. And so now my decimal is here at the end. For any spaces, I need to add in zeros to account for the place value that's being represented. So what I have here is 38016 with 5 zeros, 1, 2, 3, 4, 5, and this is going to be my number written out. Keep in mind that for a lot of number values, we like to put commas in to help us identify where the number breakouts are. So if my decimal's at the end here, if I put a comma here and a comma here and a comma here, it's easier for me to see this correlates with 3,801,600,000, and that would be the same equivalent value in standard form. So these two numbers represent the same piece of information. So it's really important to be comfortable in going back and forth with those different formats. On your assignment, you're going to need to do some problems where you're given an expression in scientific notation. So say, for example, I asked you to do 5 times 10 to the 3rd and write that in standard notation. Well, the 5 is our starting point. If there's no decimal written, remember the decimal is located at the end of the number 5. The times 10 to the 3rd means I'm going to move my decimal point 3 places, and I'm going to move it in a way that makes my number bigger. So I'm going to be moving it to the right, 1, 2, 3. Add zeros as appropriate, and I get 5,000 as my result in standard notation. If I have something like 3.2 times 10 to the negative 6, I can find that. I start again by writing 3.2 as my number. I'm going to need to move the decimal 6 places, but because my exponent is negative, I'm going to be moving the decimal in such a way that makes the number smaller. So I'm going to be moving the decimal to the left. I'm right here. I'm going to move it 1, and then I have to still move it 5 more places. So 1, 2, 3, 4, 5. There's my decimal place, and I need to put zeros in to account for all of the leftover values that still remain. So 0.4032. If you like, you might see that with another 0 in front of the decimal just to help you locate or identify the value as it goes forward. 1, 2, 3, 4, 5. Oh my gosh, 6, and another one there. I can count. From 3.2, it's over 1, 2, 3, 4, 5, and 6. Okay, so we also need to be able to go in the other direction. Let's suppose that I have a number like this, 0.00204. Anytime that you're given a number in standard notation that you want to write in scientific notation, the first thing that you need to do is find that value of A, which is a number between 1 and 10. What I do is I look for the first non-zero number that I see. Bam, right there. That's where my location of my decimal point is going to be. So I am now going to have 2.04, and then I'm going to multiply this by 10 to a power. My power is how many places I move my decimal. In this case, I'm going to move it 1, 2, 3 places to get it to there. So 10 to the 3rd. Because my original number was small, smaller than 1, I'm going to use a negative exponent to represent that value. So this is the same as, that was our original problem. Okay. Now, let's suppose that we have this number here, 90650000000. All right, lots of zeros. Let's see what we can do here. We look for the first non-zero number that we see, and we're going to place our decimal point right there. In this case, that's going to be 9 point, and you want to keep writing digits until you get all zeros. I have to write this 0 here as a placeholder and the 6, 5, but then everything else afterwards is 0, so I don't need any other additional digits here. Then I'm going to write times 10 to a power. This is a large number, so I'm going to be using a positive exponent, and I need to move my decimal point from where it exists now at the very end all the way to this spot right here. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So in this case, that number correlates with 9.065 times 10 to the 10th power.